All right, for our second look this morning, we're gonna kind of take a look at some other things associated with radiation. So one of the things that we need to be aware of is that the different types of radiation have differing effects on different kinds of matter. So, for example, um, alpha, beta, and gamma are all capable of being absorbed by different kinds of materials and passing through different kinds of materials. So, for example, alpha particles, primarily because of their size, um, we've seen in other places, size and speed tend to have inverse relationships with each other. And so, because alpha particles are so big, they tend not to travel at nearly the same speed. They tend to be a little bit more difficult to um, get to have the same kind of energy. And as a result, very simple matters like paper, your clothing, your skin can block alpha radiation from going any further, from penetrating into your body. Beta decay, on the other hand, is capable of penetrating your first layer of skin. It is capable of penetrating your clothing. It takes something a little bit more dense, like a piece of aluminum, to get it to actually be to the point where we can stop its penetration. Gamma, on the other hand, gamma has no mass. It is pure energy. And as a result of that pure energy, it is able to transmit pretty well through almost anything. Now, varying layers of concrete, varying layers of and thicknesses of lead will slow down and stop most gamma radiation. It's for that reason that when you go to the dentist and they take pictures of your teeth, they will put the lead garment on top of you to protect your organs. That's why also they, instead of being in the room with you, will usually duck behind some sort of corner and leave you in the room by yourself. The reason for that is simple: barrier protection. They are putting a concrete barrier between you, or between them rather, and the ionizing radiation. It's the same thing when you go to the doctor or the hospital. You go and get a chest x-ray, you go and get a x-ray of your arm if you think you broke it. The radiation tech is not in the room with you. Main reason they're not in the room with you is they're for their own safety. They take dozens of pictures a day, which means they would be exposed to far greater quantities of radiation than the average person. We don't want those people to die. So we put in those extra precautions to make sure that they are properly protected. They usually also have dosimeters and other things on them to kind of monitor it when they've been exposed to higher quantities of radiation than expected, or what is considered safe. When it comes to nuclear radiation and matter, there are three quantities that we would look at: mass, charge, and energy. I would actually add a fourth one on here called dose. Dosage has a lot to do with it as well. Radiation that is able to deliver its energy in the shortest possible path is the energy that is the most damaging. So outside of the body, beta radiation is considered the most damaging because it is able to penetrate that first layer of skin. And as a result, it can directly harm your skin tissues. And by penetrating that first layer of skin, it actually can get into your other subcutaneous tissues as well. Um, Inside the body, alpha radiation is considered the most damaging because even though it can't penetrate the first layer of skin, if it somehow were to get inside of your body, the heft of those molecules bombarding against your internal organs would create some significant damage. Now, the question you might be asking is, well, what about gamma? Gamma penetrates your entire body. And so the question that we have to ask there is, what is it doing when it penetrates your body? If it is ionizing radiation, that is, if it is, passing through you and, taking electrons off of places it shouldn't be taking electrons, by all means, that's dangerous. That's something that you don't want to expose to, especially not for long periods of time. But if it is just passing through your body, like right now, radio waves are passing through your body. We don't care. They don't ionize your skin cells or anything else for that matter. So, well, doesn't matter. But it comes down to, what does it do when it encounters your body? And that's why alpha radiation is the most damaging on the inside, because it's charged. So that positive 2 charge is going to naturally attract electrons to itself, which means it's going to, as it encounters your cells, draw electrons from those cells. And if you start to ionize your cells, you're going to run into other kinds of problems related to disruption of DNA or disruption of, kind of normal cell functions that can result in just simple cell death. Or if it gets into your DNA, it could resemble something where we have replication issues, and now we might have the basis for some kind of a cancer. In addition, just the mere heft of those molecules comparatively, as they are penetrating through your body, they would have to be leaving some kind of mark, some kind of damage. So our question here is this. Which form of radiation is the most damaging to your internal organs, assuming that all samples are tested outside of your body? Okay. So the correct answer here is negatron. So again, we have to ask ourselves the questions. So here, outside the body. So if it's outside the body, then we can safely mark alpha off as an option, because alpha radiation can't penetrate your skin, it can't penetrate your outer layer of your body. So it's not going to be very damaging outside of it. Now, if somehow we ingested it or inhaled it, then we would be having a very different conversation. But from outside the body, alpha radiation is not a particularly dangerous kind of proposition. For cosmic, none of you chose cosmic, which is good. Cosmic radiation would be really dangerous if we were in outer space. Most cosmic radiation is deflected by our upper atmosphere. We don't actually encounter it at all. But that kind of radiation in space is one of many reasons why astronauts have to wear spacesuits when working outside of the space shuttle or doing any kind of extra planetary or lunar kinds of missions. The other one is the lack of air, obviously, but radiation would be a significant portion of that as well. With gamma, it comes down to ionization. If the radiation is not ionizing radiation, the gamma rays just pass through us without too much problem. When we talk about radioactive decay, you start to think about things in terms of how fast are these reactions going to go. We know from our kinetics unit and from our thermodynamics unit that the key of spontaneity versus speed doesn't necessarily line up. There are reactions that are spontaneous that are not necessarily fast. There are reactions that would be fast in the opposite direction, and therefore are not spontaneous. So when we get into the kinetics of radioactive decay, we do need to understand a couple of things. One of those things is that all radioactive decay processes happen at constant measurable rates. So just like chemical reactions behave according to orders similar to what we saw in kinetics, nuclear reactions behave in the same way, which means that we can measure definitively a half-life for a nuclear reaction. And the definition for half-life for nuclear reaction is, well, it's exactly the same as what we saw in kinetics. How much time does it take for half of the sample to react? Or in this case, decay. And more specifically, we know that radioactive decays obey first order kinetics. So we go all the way back to 4 weeks ago. We remember our first order kinetics equation, natural log of our A ratios. But in terms of half-life, this second equation is the far more important one. The half-life is equal to the natural log of 2 divided by the rate constant. Important note for us here also to realize radioactive decays cannot be catalyzed. Remember, catalysis was all about pathway. There's no way to increase the catalytic pathway for a radioactive decay. Radioactive decays are very path dependent. There is no secondary pathway. So we can't just simply add a certain amount of platinum or molybdenum or some other kind of common catalyst to a decaying sample of tritium and expect that the tritium is going to react and decay faster as a result. So just kind of sum up here. Radioactive decay is first order. It cannot be sped up or slowed down. So you cannot make the reaction go faster or slower. And it obeys first order kinetics. So our half-life is a very predictable amount. What's also important about that, if you remember going back to the kinetics unit, zero order decay and second order decay included a term stating how much reactant was present. Notice that because this is first order decay, there is none of that. The decay of a sample of carbon does not slow down over time. It's a consistent half-life. And that's really good for us because that allows us to do a lot of things. In terms of calculating half-lives, because it is consistent, we're able to calculate how much of a fraction is left just by taking the number of half-lives and basically taking the starting amount and multiplying it by 1/2 to the n, where n is the number of half-lives. Now tell us how much stuff is left. So we've seen pictures like this, or at least similar to this when we talked about kinetics. But again, just rehashing the definition of half-life here. So after the first half-life, half of the sample has decayed. After the second half-life, half of the remaining sample has decayed. After the third half-life, half of the remaining sample has decayed. And so we went from 40 to 20, we went from 20 to 10, we went from 10. At the next half-life, we would go from 5 to, well, 2.5 is not possible. So we would expect either 2 or 3 there, just depending on, it's a random event too. Nuclear decay is a random event. It is a spontaneous process, both in the literal and figurative kind of translation. We cannot predict exactly when it's going to happen. We just know that it will eventually. So why are things radioactive? How can we predict when something will be radioactive or not radioactive? And to answer that question, what we have is something called the band of stability. Now, the band of stability is, if you look at this graph, every black dot on this graph represents a known and stable isotope of a particular nuclide. And what we see early on is that the band of stability largely fits along this black line here. This black line here represents a 1-to-1 ratio of protons to neutrons. And we can see that for our light nuclei up to about atomic number 20, calcium, we see that it's a pretty even kind of split. So here's the 1-to-1 line. Here are the nuclei that are largely staying on that line. And again, it's not marked specifically here, but right around here is element number 20, calcium. Starting with scandium, element number 21, we start to see a break from this 1-to-1 line, where we're seeing that the ratio is starting to become more and more neutron heavy. And the curvature of this band of stability continues to favor a nucleus with more and more neutrons. So here, at 50 neutrons, we're seeing that we're somewhere around about 40 or so protons. And so if you look at what elements are around there, you've got yttrium at element number 39 with a molar mass of about 89, and zirconium, element number 40 with a molar mass of 91. And so we're starting to see a bend, not just to 1 to 1, but starting to get closer to 1.5 to 1. And by the time we get to 82, our last well-known nucleus of origin here, lead, we can see that it is 1.5 to 1. 82 protons for lead, 126 neutrons for its most common isotope, which is lead 208. But otherwise, these colors here, green, yellow, orange, and then some down here, purple, these represent the most common types of decay. And so what you can see in these types of decay is primarily down here, before we get to the lead, we're seeing mainly beta positive, so positron emissions, and negatron emissions. And the position of each of those relative to the band of stability is pretty much straightforward. The positrons are when we have more protons than neutrons. The negatrons are when we have more neutrons than protons. Alpha decay tends to happen primarily way up here. And again, if we think about this, this makes sense. Alpha decay does not fix proton to neutron ratio, because I'm losing 2 protons and 2 neutrons. So my proton to neutron ratio basically stays the same. But what it does do is it does help the element to become lighter. And as we ditch some of that excess mass, we will eventually find our way back to this band of stability. Now, the other types of decay that happen here with fission or proton or neutron decay, we haven't really talked about those. We're not going to really talk about those. They're more on the rare cases. We will talk about fission tomorrow, because fission becomes an important part of the process of nuclear power, which is something that is gaining more and more traction and popularity here in this energy age that we are running into. But again, looking at the band of stability, we can generally predict, based upon the position, what kind of decay would be the most possible. So, yeah, again, from bismuth down, we tend to fall into either positron or negatron decays, depending upon position. Are we proton heavy or proton poor? And then above bismuth, we tend to focus a lot on alpha decays, because we need to ditch the extra weight to get back to the bismuth and lead, which are more stable. So here's a representation of what we would end up seeing in the kind of the formation of different isotopes of carbon. So carbon-12 and carbon-13 are the more stable forms of carbon. Carbon-12 is way more stable than 13, which is why it's also abundant at nearly 99% higher clip than carbon-13. But we can see that for the ones that have mass numbers less than 12, positron emission becomes an important part of that. And what we see in those cases, so just if we draw it out here, so that carbon ditching a positron would become boron. And boron 9, while not stable, because boron 10 and boron 11 are the two stable isotopes of that. It's certainly better than carbon 9 was. And on the other side, I have carbon 16, and it undergoes negatron emission. We end up with an isotope of nitrogen. Now, again, nitrogen 16 is not a stable isotope of nitrogen. But it would be able to undergo further decays to get to a position where it was more stable. And so what we'll often see in radioactive nuclei is what is called a decay series, where one radioactive step leads to another radioactive step, which leads to another radioactive step until we get to a stable isotope. So, in this case, maybe we see something along the lines of, and I'm just conjecturing here, so bear with me. Maybe this undergoes an alpha decay. And then the resulting boron undergoes a beta decay, and we end up with stable carbon 12. But we can see in the process kind of the successions here. And this is, again, theoretically speaking, yeah, I guess it's possible. I don't know if this actually happens or not. But we can kind of follow the logic of it and say, oh, okay, this was not stable. This is stable. How did I get from here to here? Well, this reaction happened, and then this one happened, and then this one happened. And this is what is called a decay series. Now, for some elements, especially some of the ones that are transuranium, this kind of thing can happen. You have a decay series that's got 25 steps in it. And each one of those steps, could end up having half-lives that are on the months to years or even seconds kind of standpoint. You just don't know. Like I said, alpha decay tends to happen most when we have nuclides that are too massive to be stable, so they ditch weight to try to come down to the band of stability. And we tend to see this with trans lead, trans bismuth kinds of nuclides. So with this band of stability in mind, which of the following would we expect to be most likely to decay through negatron radiation? So we've got phosphorus 29, carbon 14, lithium 6, and radium 226. All right, off the top here, we get radium. Since radium is greater than bismuth in terms of its atomic mass and atomic number, we can assume alpha decay is the most likely for it. Now, for the others, we can start to look at okay, well, what would happen? So phosphorus is 15, carbon is 6, lithium is 3. If I take these into negatron territory, well, the result would be 29, 16. So I've got a sulfur with mass number of 29. Sulfur is usually 32. So we took a problem where we were kind of on the wrong side we were on the proton heavy side, and we made it even more proton heavy. So that doesn't seem likely. In carbon 14, we took something that was a little bit neutron heavy, and we're going to make it even. So 14.7, this is actually a stable isotope of nitrogen. This is a really good candidate. And in the case of lithium, we're now looking at a very proton heavy isotope of beryllium. We're unlikely to see that. So negatron emission is usually for things that are neutron heavy. So A and C would be great positron kinds of emissions where we have too many protons and we get rid of some of that proton positive charge. The answer here should be B. All right, let's take a look at another. What's being shown here? All right, this one's relatively straightforward. We're looking at the emission of a particle that has a total mass of 4, and 2 of them are positive. This is alpha decay. So C is the correct answer there. All right, so what can we start to do with some of this information? Well, one of the things that we can look at is that radioactive carbon-14 is produced at a constant rate. So the formation of carbon-14 in our upper atmosphere is pretty well known and pretty well studied. In addition, there's a relatively constant amount of that isotope in our atmosphere and what has kind of found its way back down to the surface of the Earth. Why that's important is the formation of upper atmosphere carbon dioxide made with carbon-14. That carbon-14, carbon dioxide, does make its way down to Earth. It's a heavier than than nitrogen gas, and so it will naturally diffuse its way down here. And in the process of respiration, both in plants and in animals, we will see carbon 14 being exchanged by plants and being made to put into plant sugars and into other things that are eaten. And as things make their way up the food chain, that carbon 14 will find its way into animals and into us as well. So every living organism has a constant amount of carbon 14 in their body. There's nothing that we can do to stop it. There's nothing that we can do to replace it. But so long as we are eating and sleeping and breathing, we are constantly interconverting carbon 14, which means that there's a set amount in our bodies. And based on the ratios, every gram of carbon in your body, we've got about 15 carbon atoms of carbon 14 that are decaying every minute in your body. Now, you won't notice that because it's only 15 atoms per gram, and that's big nothing. But you also won't notice it because, well, you continue to eat. And so when you eat, you re-ingest carbon 14 and it resupplies the part that you're missing. Okay. Here's the thing though. When you die, you no longer are replacing the carbon 14 that you lost. And so once you stop respirating, once you stop using your bodily functions to exchange that carbon 14, carbon 14 continues to decay out of your body, but you're no longer replacing it. And so the whole concept of radiocarbon dating is the idea that we know what this ratio is in a living being. What if we find something that is not living anymore? That ratio should be the same. But we know that it's going to decay. How much has it decayed? Well, this is where that view of half-life comes in. Half-life is equal to the natural log of 2 over K. The half-life for carbon 14 is 5,720 years. So we could do a little calculation here. The natural log of 2 divided by 5,720. And we get 1.21 times 10 to the negative fourth reciprocal years. Well, how radiocarbon dating works is we take this idea and we apply that ratio. So we did this in first order kinetics. Here's how much carbon that you would have as a living being in carbon-14. Here's how much we found in the sample. We know the value of K. Solving for T, we'd get an estimate at least of roughly how old the artifact is. How long ago did it die? And so that's the basis of radiocarbon dating. That's what's going on in with regard to that. All right, so we're actually going to stop here. I thought we'd get a little bit further. I'm going to save Einstein for tomorrow, though, just in the interest of fairness to your time here. So go ahead and get that last question in. And so we will pick up tomorrow with section 3, where we're going to use Einstein's most infamous equation, the one that nobody understands, but everybody likes to quote, E is equal to mc squared, to talk about something called nuclear binding energy and the relationship between something called mass defect and energy. And we'll take that from there and we'll start talking about kind of the last little bits here out of nuclear chemistry. But that is all for today.